and today's video is on atomic trends.
So let's remember Coulombs Law of electrostatic attraction. We've talked about this one before. This is a law that gives us the electrostatic attractive or repulsive force between two charged particles. That force is K, Q1, Q2 over R squared, where Q1 and Q2 are the charges of the particles, R is the distance between the charges, and K is the constant. Here we have the charges being protons in the nucleus, they're positively charged, and electrons that are going around the outside of the atom. Those, in this case, are the charges that we are talking about. So there's a couple of things you can see here. First of all, if you have greater charges, of course, you have a greater force, either a greater attractive force or repulsive force. And of course, if you have a larger distance, because the distance in the denominator and it's squared, of course, you have less force. Also, there's a couple of other things to remember. One is that the electrons around a nucleus on the outside can shield the nucleus somewhat. Okay, let's restate that. The electrons around the nucleus on the inside can shield the nucleus somewhat from the outer ones. That is, the outer ones don't see the full charge of the nucleus because the nucleus is shielded by the inner electrons. Anyway, keeping these ideas in mind, let's look at some atomic trends. The first trend I want to talk about is atomic radius, which is really just the size of the atom, isn't it? So let's have a quick version of the periodic table here. Quickly sketch that up. And we have the noble gases on the right. So as we go down the periodic table here, we should be getting larger atoms. They have more energy shells. Each energy shell is bigger than the last, so they should be getting larger. As you go to the right, the atoms should be getting smaller because there's more protons in the nucleus. Consequently, they're pulling hard electrons and pulling electrons in closer to the nucleus in that same energy level. So, and on the right, of course, you have larger, again, the noble gases have stable octets and those are large. So the atomic radius should be going down to the right. The next trend I want to talk about is electronegativity, which is how strongly an atom pulls in the electrons of its neighbors. Its neighbor, like Martin, for example, pulling on his electron. In any case, you might remember our law from above, the Coulombs Law, which is that the electrostatic force is K, Q1, Q2 over R squared. So this R down in the bottom here, it's worth noticing that if an atom is very small, it can exert a very large force by getting its central charge very close. Okay, if an atom has got a lot of protons, it can also exert a very large force, because Q1 would be large. So high electronegativity would probably come from a large nuclear force, or a large nuclear charge, and a very small radius. So if you look at the atomic radius, the largest guys are in the bottom left, the smallest ones are in the upper right. And if you think about that for just a moment, you'd probably find that the expectation is that, well, if you pay attention to the square there, you probably find your expectation is as you go up and to the right, the small atoms, which are very small up and to the right, with a large number of protons for their size, you'd expect that they would have a very strong pull on the nearby electrons. They would have a high electronegativity. And as it turns out, this is true. So to have a high electronegativity and pull strongly on the electrons of neighboring atoms, you should be small with a large nuclear charge. So the small atoms are up in the top right-hand side, and of course the electronegativity will be down here because it gets less as you get bigger. And the electronegativity will be getting greater as you go to the right because it gets greater as you get smaller. So on the bottom left, we have the lowest electronegativity, the very largest atoms. And up at the upper right, we'd have the very greatest electronegativity with the smallest atoms. So francium, for example, down on the bottom left with its electronegativity of 0.7, it's very small. And up on the upper right, we would have, say, fluorine with its electronegativity of 4.0, which is very great. So bottom left, lowest electronegativity, top right, greatest. Here's a chart. You can see francium down the bottom left, 0.7, fluorine at the top right, 4.0. Another way of seeing this same graphic, this is in 3 dimensions, you can see the electronegativity is getting very high up and to the right, very low down and to the left. So we talk about the difference in electronegativity, or delta E neg, between two atoms in a bond. So for example, if two atoms are bonded and the expectation is that they're so-called sharing an electron, of course, if one is more electronegative than the other, then they'll share unequally. So let's make a chart. Here we have the change in electronegativity, or the difference in electronegativity between the two atoms on the left, and on the right we'll have the character of the bond. So if there's no difference in electronegativity, that is both pull electrons equally, we'd say that bond is perfectly covalent. From 0.2 up to 1.7, difference in electronegativity, we say it's a polar covalent bond. They're sharing but not equally. From 1.7 up to 3.3, we say that's ionic bonding. Effectively, the one electron has been stolen completely away by the atom that has greater electronegativity. Let's now look at a couple Lewis diagrams. Here we have nitrogen gas, and of course the difference in electronegativity between the two nitrogen atoms is 0. Each one has electronegativity 3.0, and this is a perfectly covalent bond. In carbon dioxide, the carbon and the oxygen have different electronegativities, and the difference is a difference of 1 unit, and so those bonds are polar covalent bonds between the carbon and the oxygen. Here in methane, each carbon-hydrogen bond is the same, and the difference in electronegativity is 0.4, and that is a polar covalent bond between carbon and hydrogen. Let's now look at sodium oxide. Sodium has an electronegativity of 0.9, oxygen of 3.5. The difference is 2.6. Obviously, it's a very ionic bond. The oxygen has stolen the electron away from sodium, and now the bonding is ionic. Now let's look at nitrous acid. Let's get a quick Lewis diagram going here of nitrous acid. There it is. And we'll put the electronegativities of all the atoms in. And you can see that the differences here are 0.5, 0.5, and 1.4. That bond between oxygen and hydrogen is almost ionic. 1.4 is not quite 1.7. Okay, but each bond has its own character. Each bond has its own character, and that character is set by the difference of electronegativities. Next thing let's talk about is the ionization energy. And this is the work needed to be done by another atom to remove the first electron from an atom. So the ionization energy of an atom is the energy needed, or the work needed to be done to get an electron away by someone else. Okay, so as an example, let's look at lithium. It has 2 electrons in the center there, in the 1s orbital, and in the 2s orbital has 1 electron. Okay, that one there. To take that electron infinitely far away requires a certain amount of work. That amount of work is called the ionization energy. How much does it take to remove that first electron completely? So here we have a diagram with the force and the distance. This is 1 over r squared, obviously, from Coulombs Law above. In other words, if you start with a large radius, it doesn't take a lot of force to take it all away. It's the area under the curve. If you have a small radius, you've got to do a lot more work and pull that electron much further away. Consequently, you would think yourself, and you would be right in thinking so, that the atoms that are very small have high ionization energies, so upper right, and the ones that are very large have low ionization energies. The electron's already far away, so it's easy to take them further still. So the ionization energy is about proportional to the electronegativity, generally speaking. Things that have high electronegativity have also got high ionization energy. Okay, so it turns out the energy required to remove the electron is actually an integral, and this is an idea that we get into in calculus. There's actually this sum, or as a sum of these little work elements, or the area under this force and distance curve. So it's really this area from the initial radius here all the way out to infinity. So if you get the area under that force curve all the way to infinity, that's the work, and it's the integral from the initial radius up to infinity of this force, the electrostatic force K, Q1, Q2 over r squared, integrated against r. You don't know much about calculus maybe yet, so that's okay. Don't worry too much, but just give these ideas some thought. And these trends too, it's worthwhile thinking about them, and we'll use these ideas quite a bit in our next lesson on Lewis diagrams and bonding. So just remember the periodic trends as we get into Lewis diagrams and bonding. Thanks so much, everybody, and see you soon. Don't forget to have a look at the next 2 videos in our playlist for more, and stay tuned for our next lesson, lesson number 34, Lewis diagrams and Vesper theory.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.